Okay, we're back. One more lecture to close out the day, I think, guys. I just want to go back and look at the form of the potential that we laid out in the previous lecture. And so, getting late in the day, getting tired. So it looks something like so. And remember, this was the contribution. Actually, the sum of the contributions of the attractive and repulsive parts, or attractive and repulsive components. And so use of R looks something like negative A over R to the N plus B over R to the M, where N and M are integers. Now, I got to tell you the truth, this is pretty vague. And, what's A and B? What's N and M? Those are all pretty vague. And I want to, at this stage, talk to you and take a detour and talk about what is called the Lennard-Jones potential. Now, the Lennard-Jones potential is very famous. And if Francis views this part, then he will hopefully recognize the Lennard-Jones potential in looking at his colloidal glasses. It's stated, at least on Wikipedia, that this is a simple model. Simple model that approximates the interaction between a pair of neutral atoms or molecules. All right, and that's from Wikipedia, in case you want to go and look that up. I want you to be cognizant that this is for non-bonding interactions. But what's important here is that clearly we laid out a potential earlier that was certainly a model for bonding interactions. And as you're going to see when we talk about ionic bonding, the same kind of form of this potential energy is maintained. So it's a very prolific model when looking at the interaction between objects. And a couple of things, right? A couple of historical things is Lennard-Jones. Lennard-Jones is one individual. Okay, so he's one individual, and trying to remember some information about him. he was born in 1894 and died in 1954. And he has a very short, right, a very short Wikipedia file, which is tragic in a way, since he is very an understated physicist, and many regard him. Actually, his name is Sir John. Sir John Edward Leonard Jones. And he's regarded by many as the initiator. It's a weird word. Normally at this stage, people usually say the father of, or the mother of, or the founder of, but he is regarded as the initiator of modern computational chemistry. And so he holds a special place in my heart because of that. In any case, the Leonard-Jones potential, which I'll just label V subscript Lj, is equal to 4 times epsilon sigma over r to the 12th minus sigma over r to the 6th. Okay, so we need another graph here, all right? And I want you to appreciate a couple of things here. So sometimes this is called the Leonard-Jones potential. You will sometimes hear it called the 612 potential due to the subscripts on the form of the equation above. Sometimes you might see it called the 12-6 potential. Depends on whether you're dyslexic or not. So anyway, if you were to plot this out, again, this is interparticle distance. This is V. And what happens more often than not is sometimes these are written in what are called dimensionless forms. And so I'm going to write this as R over sigma, and I'm going to write this as V over epsilon. Now, clearly from the equation above, right, we see that if sigma has units of length, then sigma over R is unitless. And then also, if we were to divide both sides by epsilon, then even before that, hopefully you recognize that epsilon has units of energy, and then V over epsilon is unitless. This happens a lot in physics, and we've encountered it a couple of times when we looked at the harmonic oscillator. We actually put that into a unitless form. And so, again, if we look at the V over E as a function of R over omega, then this is going to look something like so. Again, very much like the previous form of the potential that we looked at for interacting particles. And so, again, this is going to be 0. This will be the zero potential energy. This is going to be what is commonly called Rm, and this is going to be the minimum distance between the two particles that minimizes the energy. Okay, so it's going to be the distance that minimizes the energy. Okay, so this is going to be the distance that minimizes the energy. Okay, this part is the repulsive part, as we talked about before. This is the repulsive part. Again, due to electron repulsion plus Pauli exclusion. Pauli exclusion. And this is the attractive part. And that's complicated, as we'll see. Okay? So one can easily do lots of calculations on this 612 potential, right? One can again, let's rewrite this. Leonard Jones for epsilon going to be R over sigma over R, sigma over R to the 12th minus sigma over R to the 6th. This part is due to electron repulsion plus Pauli exclusion. This part is due loosely to van der Waals forces, or more apt, these would be called London dispersion forces. And that's your homework, actually. You know, part of your homework is to look up van der Waals forces, London dispersion forces. Okay? So one can find the minimum energy difference. I'm sorry, the minimum energy separation. Separation leads to a minimum energy. That's easy to do. One can merely just take the derivative of the Leonard-Jones potential with respect to distance, set it equal to 0. Excuse me. And find R min. Okay. So a Leonard-Jones potential is super important. It comes up all the time, and again, I urge you to go and look at the Wikipedia file on the Leonard-Jones potential and do a little bit of reading on that. Okay. So that ends our detour. We're now going to discuss bonding in terms of decreasing energy. And so the bonds that typically have the highest energy are ionic bonds. And let's take a look at the prototypical material, sodium chloride. Sodium is, if we go back and look at our electron configuration, sodium is Z equals to 11. And so that's going to be a 1s2, 2s2, 2p6, 3s1. Chlorine, which is Z17, that's going to be a 1s2, 2s2, 2p6, 3s2, 3p5. Now, I'm going to introduce some terminology here, and so this electron clearly, right, is in an outer shell, and it is somewhat easily lost. Okay, and likewise, this set of orbitals is almost filled, right? So one more electron in here, and we would have a completely filled 3p level. All right, and so what happens here is if we look at the sodium ionization energy, we look at the sodium ionization energy, and that's to take sodium 0 to sodium plus 1 electron, right? That energy is actually equal to, let's see if I have that number here readily, it's equal to 5.1 electron volts. Now, chlorine would like to grab that electron, and so we look at the energy involved in atoms in their ability to be able to grab, quote unquote, grab electrons, and we call that the electron affinity. And so the electron affinity for chlorine involves an energy which is 3.7 electron volts. Okay, and so then again, this is to make chlorine zero charge plus plus 1 electron to go to the chloride ion. Okay, so this is the energy needed. This is the energy needed for ionization, and the 3.7 electron volts is going to be the energy that is gained back in making chlorine more stable by virtue of accepting an electron to make the chloride ion. So this is the more stable entity. So some energy is given up by that process, and so overall, then the energy net, so to speak, is going to be 5.1 electron volts minus 3.7 electron volts, where we need 1.4 electron volts, right, to make sodium plus and chloride chloride negative simultaneously, right? So we need 1.4 electron volts. That 1.4 electron volts is called the activation energy. It's the energy overall that is needed to form the sodium ion and the chloride ion, okay? So we need 1.4 electron volts, okay? Now, what happens is, again, not going into the particulars here, but the energy now that is required, that is the 1.4 electron volts, is the, as I said, is the activation energy. And so what that looks like now, graphically, is the following, right? So what happens now is here's what happens. So we form the sodium ion, we form the chloride ion, okay, and so this needs 1.4 electron volts. 1.4 electron volts. But what happens in the process here is that once these guys are formed, there's going to be an attraction, an electrostatic attraction, and that energy is going to be much greater than this 1.4 electron volts. As a matter of fact, one could calculate that pretty easily, right? So the bond distance between these two is about 0.24 nanometers. And if you were to use simple electrostatics, right, that energy would be equal to 1 over 4 pi epsilon 0, the charge on the sodium ion, the charge on the chloride ion, over the distance between them. And so if you were to actually put that in there, now the charge on the sodium ion is equal to the charge of the chloride ion, which is 1.6 times 10 to the negative 19 coulombs. And R now is equal to about 0.24 nanometers. If you were to plug that in there, you'd get an energy which is about 6 electron volts once you converted from joules to electron volts. So that's the energy that you would get to offset this energy needed, right, for generating the sodium plus chloride ions, right? So that actually this electrostatic attraction then has enough energy to overcome the activation energy needed, which means that at the end of the day, the energy net is about 4.6 electron volts, okay? And that now is the binding energy, right? That's the binding energy. The binding energy for sodium chloride. Okay, now what does that look like graphically? Let's go in and take a look at this. Take a look at this graphically. Now, so this is R, and this is we'll put this in nanometers. This is the total energy, and this is in electron volts. And so this is 0 then, electron volts. This is, -1, -2, -3, -4, -5. Okay, this is about 0.2, 0.4, 0.6, 0.8, and 1 nanometer. And so the energy curve that results from this, and again, these are both theoretically and experimentally determined, looks something like so, right? 0.24, so looks something like so. So this comes up just about like that. Okay, so this is about 0.24 nanometers. Okay, this energy from here to here is the binding energy, and we said it was about 0.4 or 4.6 electron volts. Actually, experimentally, this is about 4.2 electron volts, right? So this is not too far off from our quick calculation of above. Okay, so this is where dissociation would occur. Okay, and from here, this would be where sodium chloride would dissociate into sodium ions and chloride ions. Okay, so this gives us a little bit. This gives us a little bit of an understanding of ionic bonding, and again, these 4.2 electron volts is the energy needed for dissociation. Okay, so let's end there, and we'll pick it up with covalent bonds and then van der Waals bonds. Some really interesting things to talk about there, and I will also give you some needed conversion factors next time. And don't let me forget, of course. All right, take care, guys. Have a good evening.